Hello everyone, this is Chanchal Roy from University of Saskatchewan. My area of interest is generally in software maintenance and evolution, empirical software engineering, building software recommender tools. So we make tools and techniques for software engineers so that software engineers can uh, maintain software better. So they can develop software that is sustainable, that is evolvable, that is scalable, and that is cost effective. So one of my areas is software clones. In my today's talk is focused on software clones. And if somebody is interested to more about my other areas, they can visit my webpage. So what is software clone? Software clones are kind of similar fragments of code. So if you have a two piece of software, two piece of code, for example, by some, and they're similar to some definition of similarity, maybe we can call them clone pair. If there are more, we can call them clone class. Right? So let's see this video from Wikipedia. So copy and paste is very common in software development. So developers copy a piece of code, they paste it somewhere else, and they can reuse it by making some modifications. And that happens most of the time. And there are different types of those modifications. So based on that, we also have different types of clones. If you have this original fragment here, then somebody could copy and paste and then reuse just exactly without really changing any syntax or anything. So here now you see someone is using them, just changing their comments or just making some white space. And also like here you see, if you after copy and paste, some people might change the variable names, the identifiers, or even the data types. We call them type 2. And then we have type 3, which happens the most. And this is where you copy and paste, and then maybe you make significant modifications like modifications lines, addition of new lines, or deletion of lines. And it's not only for one, it happens for, it could go, as long as you need for your context. And there is another one which is called type 4. So they might not be similar as per their context by their syntax, but they might be functionally similar. For example, like look at this example, it is for loop and this is in while loop. So this is called type 4. So the question is, are there really clones in the system? And the answer is yes. Sometimes the clones could be 50% in the software systems. Why there are so many clones in software systems? The answer is obvious, because copy and paste is a common practice. And also, of course, it is very simple to reuse a piece of code from existing one. You can just take something from a stock workflow and maybe you can use it for your context, right? Sometimes developers are given time limit, so they are forced to make copy and paste. And another interesting aspect is, of course, if you have something already working, you feel confident reusing it by copy and paste and by making changes, right? Sometimes some languages, of course, do not allow you to do procedural abstraction and you are forced to make copy and paste, right? So question is now, there are clones in the system, and because there are reasons for clones to be in the system, the question is, are they really harmful? Do they really matter? The answer is yes, clones do matter, because if you have clones, for example, and if you're going to make some changes to one of them, maybe you're not making the same change to the other. And then you are going to make inconsistent changes. And inconsistent changes to code duplicates are actually frequent and could lead to severe unexpected behavior of the system, right? And this is a number one bad smell in bacon floors list. And like, think about another example. If you have a bug in a code fragment, and that code fragment is being copy and pasted over and over to different places of the software systems, that means you are actually propagating the bug, right? And that could cost trillions. Accidents could happen, like self-driving cars and so on, right? So there are a lot of issues with clones if you have similar fragments of code in software systems. On the other hand, as we already saw, clones are good. Clones are kind of a principal re-engineering tool, like Godfrey's group was talking about it. And clones are often intentional, right? Not really all of the clones are harmful, and rather they could be useful in many ways. And sometimes it is impossible to take care of some of the clones, or maybe not practical to remove them. So that's why the overall goal is to actually manage the clones. Like manage the clones means safe cloning. So you let them do cloning, but you can help them to doing it better so that they do not make inconsistent changes. Or if there are already clones, maybe you can help them to refactor it properly. Or maybe if they're not really refactorable, you can help them track the clones over the evolution so that you know if you are making a changes to somewhere, so that your changes will be automatically propagated, or at least it will notify you where to make the other change, so that you are not going to introduce like copy paste or inconsistent change errors. So there are of course a lot of clone detection tools, and you can make clone detection tools by tracking your copy paste operations. Sometimes you do just metrics comparison, sometimes you just directly compare the text, and there are a lot of other ways you can find out the similarity between two fragments, including graph. A lot of clone detection tools. Right now, I think there are over 200 clone detection tools. And those tools detect clones. Some clones are good, some clones are bad, good shape and bad shape, right? So we have to figure out, for the management, we have to figure out what are the good clones, what are the bad clones, and how to deal with them. There are also another aspect, and which is really getting very, very popular and important nowadays because of the data we have, is large scale clone detection. And people have tried, people have applied clone detection for license violation detections, for building new libraries, for API recommendation, for code completion, for code search, right? But the problem was that these tools can only detect, for example, mostly type 1 and type 2 clones. The question is, how do we really detect type 3, and how do we detect from very, very large data set? We had a paper which is with our collaborators at ICSI, Sorsara RCC, that could detect large scale clone, like from large scale interproject repositories. And further to that, actually what we did is called another tool we developed is called CloneWorks. And this is even kind of designed to run on a standard hardware. So you can detect clones from interproject clones and from maybe a lot of systems, but you do not need that dedicated hardware, maybe even from your laptop. So we have, and this tool is also targets near-miss clones like type 2, type 3. Those are even difficult to detect. And it is also flexible. Like you can modify the tool, you can modify its input, you can modify its output, you can not only detect clones, maybe you can detect API usability patterns and so forth. You can customize it very, very well. Of course, we have a lot of clone detection tools, and we do not know which tool is really good and which tool is bad. That's why we have to also measure, we have to evaluate the performance of the tools. And because they're IR-based techniques, mostly it's kind of this domain, IR-based domain, clone detection. So we have to measure them in terms of precision and recall, right? Of course, we can measure the precision maybe by validating a small sample, but measuring recall is kind of challenging. And most of the tools people publish, they kind of try to avoid measuring the recall because of the challenges. How do we really, find out the recall if we do not know how many really actual clones are there? There are a tool called by Balloons, but in the same time, like Balloons benchmark, and that has a lot of issues that, for example, Becker pointed out in her TSC 2007 paper. So let's say this one, measuring recall, right? So if you want to measure a recall, if your tool gives this set of clones from a subject system from this one, then if you want to measure a recall, the recall will be only the intersection of the benchmark. And this benchmark is very challenging to have for a system, because you don't know, how do you know for a system this is a benchmark? Because again, this is very challenging. I will talk about it a little bit more, why it is challenging. And on the other hand, precision, actually you can manually validate maybe by some people and see whether they think about it, whether they think it is good or bad, right? So why it is challenging to measure a recall, for example, or to have a benchmark for clones, because we even do not know what is the actual definition of the clone. And you need a lot of manpower to validate clones. And even for a small system, large system is very tough. Even for a small system like Cook, If you really want to just for look for function level clones, then you will have to validate about 1 million pairs. And if you go for like fragment levels, then maybe billions, who knows, right? And humans are also error prone. So it's not easy to do error free. And for that Baker, for example, if you took Baker raised the concern from Balloon's benchmark because it was like 77 hours, 2% only validated, but there was no reliability of the judges, no guarantee that because it kind of used a union result of different clone detection tools. So you have to have you have to kind of only looking for your benchmark is only for by the combination union result of those clone detection tools. So like if somebody is coming from outside of this set of clone detection tools, they will not be performing well for this benchmark because the benchmark is created for those tools, by those tools, right? So that's why what we did, we tried to do an automatic approach, like synthetic clone benchmarking. So and we call it mutation injection based framework. So what we do, we have original code base, and then we randomly pick some of the code fragments, and then we randomly modify them based on some mutation operators. And then we inject into the system, original system, and we make thousands of revisions, thousands of kind of copies, mutants based on those mutated fragments. And now that we have those thousands of mutated fragments, now we use different clone detection tool, and we try to figure out whether those known injected clones could be detected by a clone detection tool. And this process is completely automatic. The problem with this benchmark is that it is kind of artificial. So the mutation operators we do may not reflect the real clones, right? So we follow kind of a taxonomy, but this taxonomy might not be reflecting the real behavior of the developers in making clones. That's why what we did, we made another benchmark, which is called BigCloneBench, and that works with real world and large scale interposer clone benchmarking. And with that, we kind of did 25,000 Java projects that has 250 million lines of code. And we kind of manually followed a functionality-based approach where we think of possible implementations of a certain functionality, and then we think of what are the source terms, and then we look for those terms in those 25,000 Java projects, and then we manually validate by a lot of users, a lot of people to validate which are actually good one, which are actually similar, and which are not for that functionality. And we have done it for 48 functionalities, and there are about 8.5 million true clone pairs in our benchmark, and 290K false clones. Of course, we also have a tool to use this benchmark, which we call BigCloneBench, and people can easily use this benchmark to evaluate their clone detection tools. We also have a web version of it. We call it BigCloneUI. So for this one, you can just upload, or you can just use your clone detection tool result for it, and you can easily compare your result with other tools on the web. Some of the tools can be found in this slide. The link of the can be found in this slide, and you can go on and you can check online. Of course, for clone validation, we also have a tool, because validating clone is not also easy. It's error prone and it takes time. So we tried to have an automated approach. We followed a machine learning based approach, and using that BigCloneBench, we learned from BigCloneBench, and then we tried to build the benchmark using CNN. And also this can be you can also make benchmark with it on the fly. You can just, detect tools, incorporate it into this, and then you can validate them and you can make the benchmark. So you can do both. You can learn, and also you can make validate clones and also make your own kind of learning method as per your context. So I'll finish this talk with kind of a visionary scenario, how and where we could go with this cloning research. Okay, so let's see this one. I think many of you know this person, right? And that person, see, So this person is talking about you are editing a clone and your change is inconsistent. I said, do I? So what? Well, you changed it about 6 months ago already. Your change was inconsistent. I told you so, but you ignored me then. You said this clone should evolve independently. This bug has gone unnoticed in the test, but caused a failure for a customer. Oh, I forgot. What do you suggest? You have multiple options. You can refactor it. You can make your change and I can check it for consistency. Or you can continue ignoring me. I will show you the consequences of these respective actions. So these are the actions. So if there are 3 different parameters in terms of the quality for those A, B, and C of the option above. So defect prone, readability, change effect, testing effect, all those different things. Are you thinking I have to change this code in future? Well, of course I do. My estimate is based on the change history so far. So looking at the change history, I can see that you will have to change this in future. I will never change this code again. Based on my past history, the likelihood that you are wrong is 85%. I'm sure you are going to change it. And I'm 85% confident. Okay, I do not know how to weigh these factors. Tell me in dollars. Well, my estimate is for cost and savings are like for your option A, B, and C are as follows. If you kind of refactor it, you will save a lot of money. And if you ignore me, you might need thousands of dollars Bitcoins in future to overcome that problem. Okay, let's refactor it this time. How should I do that? Okay, it's a type 3 clone. Difficult, let me think. After 1 minute, it says, I found a solution. Please apply. Any other clone to fix? No, they are all okay right now. I am pretty sure that most of them will not change, and those who are too complicated to be refactored. Leave them as they are. I come back when you edit them. And finally, this is kind of a taxonomy or kind of a graph, as you can see here. So as you see in this slide, there have been a lot of work in clone detection technique area, like clone detection, documenting clones, analysis, visualization, annotation, recommendation, refactoring, refactor scheduling, refactoring verification. But on the solid side here, on the inner circle, we have done it mostly for type 1 and type 2 kind of thing, or most of the things we have done it for type 1. And then many of the things we did some of those for type 2, some of those, we increase a little bit more. For some of the cases like detection, we have done well, for example, in type 3, but we have not really done very well. Still, you see it's not solid. That means we have not done very well for type 4. Similarly, for other things like tracking, we have done it very well for type 1, a little bit more for type 2, type 3 maybe until, but type 4, because we even cannot detect them properly, right? So similarly for all other things, it is not so easy to deal with all those problems in clone detection and analysis and management area. So there are still a lot to do in this area. So I thank you, all the people who is listening to this talk. I know that this is a difficult time. This is kind of time we are all suffering. I wish all of them very best. And at the end, I should say that we are looking for a lot of PhD and MSc students, and we are also looking for postdoctoral positions in software analytics and software clones, building recommender systems in software engineering, mining software repositories. So feel free to contact me if anyone is interested, or please feel free to recommend potential students on postdocs and refer to me. Thank you all so much.